Hello everyone, welcome to my class. My name is Partho Das, Assistant Professor, Department of Electrical Engineering, JIS College of Engineering, West Bengal, India. So today's class we are going to do several problems on RLC series and parallel circuit. So in the previous classes we have already discussed about the theory and the concepts regarding the RLC circuit. So in today's class we are uh, going to solve different problems regarding this, and we are going to know what is resonance and those things, and conditions and problems at resonance condition, what is happening, what is the characteristics, those things we are going to do right now. So let us start with our presentation. Yes, series resonance. So first see what is written over here and what we are going to learn today. So in a series RLC circuit, series resonance occurs when XL is equal to XC. The frequency at which resonance occurs is called resonating frequency and is designated as F suffix R, small r. After completing this section, we will be able to understand the analyze a circuit for resonance, define what is resonance, that we'll able to understand, that impedance at resonance condition, that we are able to understand, explain why the resonance cancelled at resonance, that we'll able to understand, determine the series resonating frequency, that we'll able to understand, calculate the current, voltage and phase angle at resonance. So everything already, whatever problems we have done, so already we have whatever problems we have done, whatever theory we have discussed, so everything we will do, but we will find out those things at the resonance condition. So first we will we will just think why this resonating condition occurs in RLC series circuit, but it is not occurring in the RLC in DC circuit. Why? So think from the first. So basically first, resonance cannot be occurs in the DC circuit as it doesn't have any frequency. Second thing, as it has no frequency, so XL and XC cannot work over there. So in DC circuit only resistance can work, but in case of AC circuit we have RLC, all components, and in between this R, L and C, so we have another two reactance components, that is with respect to this, from A we can find out the XL, that is the inductive reactance. From the value of C we can find out the capacitive reactance, that is XC, so that we need to find out the impedance of any RLC circuit. Okay, so that thing we have to do. So now why resonance occurs in RLC series circuit? The point is that in RLC series circuit, excuse me, as it is a frequency dependent component, so when frequency is changing, at that time XL and XC is changing. Why it is changing? Because in case try to remember the formula of XL and XC. XL formula is given by 2 pi Fl and XC formula is given by 1 by 2 pi Fc. So these are the two different equations. So in case of, as we can we just think 2 pi is a constant term, so it doesn't have any effect. So phi the f is the frequency. So now this f has uh, if we change this f value in case of XL and XC, so there we can say that XL, in case of XL the frequency is directly proportional, in case of XC it is inversely proportional. So with the change of frequency, the point is, with the change of frequency this XL and XC is changing, but they are changing in the opposite direction. So try to think, XL is equal to 2 pi Fl, it is directly proportional, so we can say that with the frequency XL is directly proportional. Correct? Now What is Xc? Xc is equal to 1 by 2 pi Fc. So here Xc is inversely proportional to the frequency. So now think, if we increase the frequency, so what will happen? So XL, when in case of XL, the when we are changing the frequency, so say we are increasing the frequency, so when frequency is increasing, XL is increasing. But in case of Xc, what will happen? In case of Xc, as it is inversely proportional, so what will happen? When frequency is increasing, it is inversely proportional Xc, so it is decreasing. So frequency is increasing, it is Xc is decreasing. So it will happen. So that means when frequency is increasing, so we can say that XL is increasing and so XL is increasing and Xc is decreasing. So at some point it will appear when both has the same value. So that means when frequency is increasing, maybe decreasing. In both case, at a certain point will appear, certain frequency value will appear when that the value of XL and the value of XC both are same. Now, if both are same, what will happen? Think the formula of impedance. What is the formula of impedance? Z is equal to under root r square plus xl minus xc whole square. Correct? We know that this one. Now we are telling that xl and xc has the same value. That means what? That means we can say that there is no difference between xl and xc. So the difference xl and xc is going to be eliminated. So what is remaining? So that means we can say that when this resonance occurs, that means when the value of XL and XC is equal, at that time the impedance of circuit of that particular circuit is equal to the resistance, isn't it? Because at that time from the equation XC and XL is cancelling out. So what is remaining over there in the equation? It is the resistance. So what is the total thing what we have I have discussed, that is due to the change of the frequency, resonance occurs. When resonance occurs, XL value is equal to XC value, and when XL value is equal to XC value, at that time the impedance of the circuit is equal to the resistance of the circuit. So you can say that XL, that is inductive reactance, and capacitive reactance has same value. That means uh, it same value. That means it doesn't have any effect in the circuit. So at that time the circuit is a purely resistive circuit. So now, so it is, see, the coming to the diagram, so it is very important. So series resonance XC, like, okay, first diagram, there are two diagram we can see over there. One, in the left hand side diagram we can say that the RLC, all are components. In the right hand side there is a R comp present over there, and there is a source, is AC source is connected with that one. Now in this source we have a frequency, say in the Indian standard scenario it is a 50 hertz. Now by some means, by some audio frequency generator, by some other frequency changer, if we are changing the frequency, so what will happen? The value of XL and XC is going to be changed, and at a certain point the value of XL and XC will be equal. So it is shown, follow my pointer, it is shown over there. When the XL and XC value is equal, so at that time the circuit behaves like this on the right hand diagram. Follow my pointer, this is the right hand diagram. That means at resonating condition, so at so one very important thing is there. So at certain frequency this phenomenon is occurring. So that particular frequency is known as the resonating frequency, denoted by f suffix r, fr. Okay, and at that time the we can conclude that, we can say that as XL value is equal to the XC value, so at that time the impedance value is minimum. So if we say that if the impedance value is minimum through any circuit, so what is the maximum? The current is the maximum. So so what we have so now what is known to us? So at series, in the RLC series circuit, when these things occurs, that means when resonance occurs, at that time the impedance of the circuit is minimum, and as the impedance of the circuit is minimum, so the current in the circuit is maximum. Okay, and if we when we will do the RLC parallel circuit, there we can find out the condition is reverse. What is the condition is reverse? That means at that time the impedance is not minimum, it is at the maximum condition. So at that time the current is minimum in case of RLC parallel circuit. Okay. So already in the previous class we have discussed. Okay, first coming to some problem. So what is written in the problem? So that thing we have to do. For the series RLC circuit in figure 1810, determine XC and Z at resonance. Correct. So whenever this kind of problem is there, so it is told that determine the value of capacitive reactance and impedance, both at which condition? Resonance condition. So at resonance condition, what we know, at resonance condition XL value is must be equal to the XC value. So we can put that thing over there. So in this particular problem, XC value is not given, but XL value is given. Now if we know the concept, what is the concept? The at resonance condition XC value must be equal to the XL value. So if it is known XL value is 500 ohm, so definitely this XC value will be 500. So that's why it is written that in the solution XL is equal to XC at resonance frequency, we know, and thus XC is equal to XL, that is 500 ohm the impedance at resonance condition. Correct? Getting my point? Okay. And at this condition, what is the impedance value? So impedance is given by R plus JXL minus JXC. So here XL and XC both have the same value, so definitely it will be cancelled out. So what is the remaining? 100, or that is the resistance value. So by combining these things we can find out the result for the impedance at the resulting condition. Now if I ask you, find out what is the current at the resulting condition if provided the voltage value is given. So just say the voltage value is given 100 ohm, sorry 100 volt, and it is told that find out the circuit current. So what we are going to do? So we know that in AC circuit what is the current formula? V by Z. So in case of at resulting condition, we know that Z is equal to R. So the formula is reduced to I is equal to V by R. So as V is 100 volt, so we know the resistance value. So if we put that value over there, so we can find out the current value over there. So next, yes, this is the series resulting condition. Yes, very important derivation is this one. For RLC series circuit, we know the condition is XL is equal to XC. So that means that now we are going to find out that what is the frequency value at that particular time. So for that, what we have done, we have um, placed the expression of XL and XC over there. So what is the expression for XL? XL expression is 2 pi FRL, and XC expression is 1 by 2 pi FC. So now if we take only the frequency in the left hand side and other component in the right hand side, so what we will get? So FR square is equal to 1 by 4 pi square into L into C. So take the root of that equation. So we will get FR is equal to 1 by 2 pi root LC. So this is the formula. So this direct formula, this derivation is important for your semester. At the same time, this formula is very important. Why? Because using that formula you can solve different problems. Say in a particular problem, it is told that there is a RLC circuit. R value is this one, L value is this one, and C value is this one. Find out at which frequency resonance will occur. So what we are going to do? So we know the formula. What is the FR formula? FR is 1 by 2 pi root LC. So in that particular formula, we will place the L value and C value, and after putting that value, whatever result we will get, that is the particular frequency at which for the particular circuit the resonance will occur. So now let us check a second problem. Yes, what is written over there? Find the series resonating frequency for the circuit in the figure 1812. So what is there? So there is a circuit. See, one important thing is there. See, both sides there is a ground. What is the significance of this? That means it is showing us as a complete circuit. Without ground, it is not a complete circuit. So there is a AC source Vs, it is denoted. There is a resistance R 100 ohm. There is a C capacitance, that is 50 picofarad. L is the inductance, that is 5 millihenry. So we know that it is told that the resonating frequency we have to find out. So how we can find out the resonating frequency? So to find out the resonating frequency, we know the formula. What is the formula? Fr is equal to 1 by 2 pi under root Lc. So we know the L value and C value. So we will just put the value and we can find out the result. But a little thing I should remember, I should tell you, that is, see, the capacitance value and the inductance value, they are in picofarad and millihenry. So there the units are not same. So we have to convert from picofarad to farad and millihenry to henry, and then find out the result. Otherwise, if you doesn't do this, otherwise it will be a the answer will be wrong. So in any case of this kind of problem, so RLC circuit, in case of maximum case of this capacitance value, inductance, they are in pico, micro, nano, in that range farad, and this Henry in milli, mainly in the milli Henry or Henry, sometimes it is 0.202 Henry. So like this way it will. So my point is, so make all the parameters in the same unit so that you can calculate and the result is correct. So if we put the value, so we can find out um, the resonating frequency values. Okay, so here also we can find out the different many things. What are the different many things? So we can find out the voltage at that time, voltage across the resistance, across the capacitance, across the inductance of all the components. How we can find out? So at that time we can so VR, what is the formula? The voltage across the resistance, definitely Ohm's law, I into R. What is the voltage across the capacitor? That is I into I means the circuit current, as it is a series loop, so a single current is flowing, so we are considering that single current is I. And in case of VC, that is the voltage across the capacitor, the formula will be I into XC, where XC is the capacitive reactance. And same way, in case of inductor, what is the voltage across the inductor? It will be VL is equal to I into XL. So from capacitor, capacitance value, that is from 50 picofarad, from C2 we have to find out the XC, from L value we have to find out the XL. So after finding out those values, we just put with the equation I, and now before that we have to find out the I value. So it is very simple to find out the I value. Why? Because at the resonating condition we have to find out everything at resonating condition, correct? Because the problem is at that condition. So when we have to find out the values at the resonating condition, so at that time the current formula will be V by R only, not Z, because Z is not applicable there. And if we put Z at that time resonating condition, Z is equal to R, so no change is there. So first we have to find out the current I, that is V by R. After finding out that I multiply with R, it will give us the voltage across the resistance. That I, if we multiply with the XC, that will give us the voltage across the capacitor. And if we put multiply this L value with so not L value, XL value with this current value, we will get the voltage across the inductor. So these are the things. Like this way we can think about of this problem, and we can solve any kind of problems. And one more thing is there. As L at resonating condition, L and C, as it is, as both are not working condition, So it is not working, I should say, rather say it is not effective at that moment. So we can say that as the resistance is working only, so must not be any leading or lagging, there must not be any phase angle. So we can say that in RLC series circuit, when resonance occurs, the circuit has at unity power factor. It is working at unity power factor. So very important objective question this one, or you should say this is very important for the understanding how the circuit behaves when a circuit a resonance occurs, maybe series, maybe parallel resonance circuit. In case of parallel resonance circuit, the equation is different, that will do later one. The solution techniques are different, but the Q factor or bandwidth, those equation will remain same. So this is all about the RLC series circuit that we have discussed in this particular class. In the next class, we are going to discuss about the RLC parallel circuit. And I think after this session, you are able to understand what are the equations we have, what is the conditions of basically what is the condition of resonating frequency, and when resonance occurs, what happens with the circuit, what are the characteristics appears in the circuit, and related problems that we have solved. So this is all for today. Thank you.